Hi, everyone. This is a introduction to magnetism. So we're talking about how magnetism actually is related to electricity and stuff of that sort. So I thought I'd start off with just giving you a little intro to what Oersted discovered. We had known for thousands of years that certain materials tended to align themselves in weird ways and stuff like that. And that was first discovered in a part of what would be modern day Turkey, and it was called magnesia at the time. So that's where we got the word magnetism from. But for some time, and not until the early early 1800s, did we actually start to figure out that there was a relationship between electricity and magnetism, and we had been looking for that. And that was partly by Oersted, who discovered that when a current goes through a wire, it would actually create a magnetic field. The magnetic field is actually in a weird way, though. So if you imagine this pin as if it's a current carrying wire, and we'll say the current is going in the direction the pin points, so up. If you now grab that pin with your right hand, your thumb pointing in the direction of the current, your fingers curl around it in the direction that the magnetic field line points. So you can see if the current's coming towards you, like it is here for me, if the current's coming towards me, then it goes in a counterclockwise direction, as if and basically making the magnetic field lines making concentric circles, the center of which is the center of the current carrying wire. And the farther you get out, the weaker it is. So that's the first thing we need to know. Then that, of course, related electricity to magnetism, because we knew currents were caused by charge carrying wires. Then it just became a matter of us realizing how those two related, in terms of, could you make a magnetic field from an electric field? Could you make an electric field from a magnetic field? And if so, how? Obviously, if we've got an electric field driving a current, and a current creates a magnetic field, we've already done part of that. So just remember, when you grab a wire, imagine grabbing a wire with your right hand and your thumb pointing in the direction of conventional current flow, which is which directions the positive currents would go. You grab it with your right hand and curl around, and then the direction the current goes is basically the same direction your fingers curl around that current. So if the current's coming out of the screen, you'd see that it's actually going in a counterclockwise direction. If the current is going into the screen, or excuse me, in my case, if the current's going into the screen for me, then that's actually coming out of the screen for you guys. But either way, the main thing is if you're looking at the current and it's actually coming out at you, then it's counterclockwise. If it's going into the page, it's going clockwise. So I'm going to represent that with a drawing. So let me start off with switching cameras. So the way we indicate a vector pointing in or out of the page is we actually imagine it sort of like an arrow. So if we're looking at the tip of an arrow, meaning an arrow like from a bow and arrow, it should look like basically a circle with a dot in the middle, and the dot would be the sharp point. And if we look at the back, we'd see those little feather things that hang off the side, so it look like an X. So what we'd say is, if we wish to draw, imagine a current carrying wire, let's say right here, there's our current carrying wire. If we want to say the current's coming at us, we'd say that's the current coming out of the page. Whereas if we wanted to imagine a current going into the page, we would draw it like this with an X on it. Okay, so that is, trying to focus that a little bit, that is what current coming out of the board looks like, or going into the board looks like, and this is what current coming out of the board looks like. Current coming out of the board, of course, if I grab that with my right hand, such that my thumb points in the direction of the current, which is up towards the camera in this case, then you see the magnetic field lines would be concentric circles whose center is the center of the current carrying wire. And what that means is, if you put a little compass over here, then at this point, the north would point that way. At this point, north would point this way. At that's this point. That's this point. At this point, north would point that way. and at this point, north would point that way. Okay. Similarly, if you had a current carrying wire with the current going into the page, we do our right hand rule thing again, only this time our thumb's pointing into the page with it, and we see that our fingers are curling around in a clockwise direction. So in that case, we'd make a concentric circle, and it would go clockwise like this. So if we put a compass here, the north part of the compass would point this way. If we put it here, the north part of the compass would point down. If we put it here, the north part of the compass would point diagonally that way. Here, it would point to the left of the compass. Okay, so that's something else we learned. We learned that basically magnetic field lines point in the direction that a north pointing magnet would align itself. So there's another magnetic field that we know in everyday life, and that's actually the magnetic field of the Earth. So if you imagine the Earth, and let's say its rotation axis is just vertical, which is obviously tilted with respect to the plane of the planets, but we're going to imagine this is just the North Pole, and this is the South Pole, and maybe this would be California, and Gulf of Mexico, and Florida, and North Carolina coast right there, Cape Hatteras, and now we're up here at Maine and Massachusetts and all that good stuff. Okay, so if you look at it that way, it turns out the Earth has a magnetic field that acts like it's actually a bar magnet inside of the Earth. Only our north poles of our compasses point us to the north. So in fact, as you probably know from dealing with magnets already, south poles align to face north poles, and north poles align to face south poles, and vice versa. So in fact, since our north pole of our compass is pointing towards the north pole of the Earth, the actual north pole of the Earth is a magnetic south pole. And it's also tilted with respect to the axis. It's not aligned. And in fact, what's worse is it moves on the order of miles per year. And it's probably flipped directions about every 800,000 years on average over the last 350 million. It's probably flipped directions, meaning the South Pole that is currently in the north would be in the south, and the North Pole that's currently in the south would be in the north, and back and forth like that. So that's another case. We don't exactly know why these magnetic fields are caused. Sometimes people will say it's the dynamo effect. That's just putting a word on something to explain something that we still don't really know that much about. One thing we think is involved is ions that happen, for instance, when a core of a planet becomes molten liquid, it gets so much heat that the electrons are likely not to stick to the individual atoms. So they become ionized, and then a rapid rotation. So perhaps a liquid core with a rapid rotation is one of the necessary, or two of the necessary ingredients to create a magnetic field in a planet or a body or something of that sort. So we have a north pole of the Earth, and as we said, the vectors that make up what we call the magnetic field actually point in a direction. Basically, they point in a direction that come out of the north and into the south. So like this, and there'd be another one here, of course, would be smaller, and there's no real magnetic field that's perfectly parallel to the ground at any particular surface. It's always inclined by some angle, and since the North Pole doesn't perfectly align with the south magnetic pole that we call the North Pole, there's always a slight deviation from that. Whereas if you use the North Star, at least over the next several hundreds, maybe even on the order of a few thousand years, you're probably going to get a fairly accurate result in finding north, but the North Magnetic Pole is not quite as reliable as that. So what we know is magnetic fields point from north to south. So if we actually had a north pole of a magnet right here, and we had a south pole of a magnet right here, then what we draw is the magnetic field lines going like this. Okay, so that's the way they point. Now, in addition to understanding that information, we also need to know, what do magnetic fields do to current carrying wires? Well, it turns out that if you have, let's imagine a current carrying wire going through a magnetic field in whatever direction. Let's say the magnetic field, we'll call it a uniform magnetic field, or at least we'll consider uh, a part of the wire that's small enough where the magnetic field doesn't change very much. So that's our magnetic field. And let's take this itty bitty piece of the wire. By the way, we're assuming the current is going this way, which will come in handy in a second. And let's take this itty bitty piece of wire right here and represent it by this little piece of, or this little vector DL. Notice the DL points in the same direction as the current goes. When that's the case, then we found that there is an actual way to find the force of a current carrying wire on a current carrying wire as a result of a magnetic field, and that is that small amount of force on that small segment of wire is actually equal to the current times that DL vector, that little unit segment that's tangent to the wire for some period over a small distance, crossed, that's an actual vector cross product with B. So in this case, you can see there that if this is really a two-dimensional drawing, which we shouldn't think that way, then they would actually be parallel. And of course, cross product of any parallel vectors always gives you 0. But if you imagine that this DL is actually tilted in some way, then you can see that it wouldn't be 0. But that's the actual equation. DF is equal to IDL cross B. Now, I'm going to try to focus this again because the drawing's not looking as clear as I'd like it to be. Now, what happens if you get a simple case of, let's say a magnetic field, and let's say it's fairly uniform, so it doesn't change much, of course, over the size of the wire that we're investigating. And in fact, we're going to say the magnetic field is pointing into the page like this. And let's say we have a wire that's actually not in the page like that, so it's not perfectly perpendicular. It might even be tilted at a certain angle, but still we're going to say the wire goes like this. It's a nice straight wire. The current's coming out of it in that direction, and what we want to know is what would happen in that case where it's so much simpler. Now if I look from the side, I would say, okay, let's say this is horizontal and this is vertical, and what we might see is that the magnetic field lines, B, are going like this. Okay. And that's these guys. And what we'd see also is that the current carrying wire is at some angle, let's call it phi. Okay. And then I, of course, is coming out this way. So in that case, what do we get for the expression for the force? Well, as you can tell, in this case, the IDL, I is a constant. DL, in fact, is going to be this little segment, but then we're going to integrate that over all the little segments, so it actually becomes the length L, or at least the part of the length that's submerged in this nice magnetic field. So we end up getting DF, which is equal to the integral of I dl cross B. Well, since B doesn't vary much, we're really just going to take a cross product of L and B. And the cross product, the way it works is you lay your finger, your pinky finger, say, along the DL vector, and you allow your fingers to curl in the direction of the B vector, so like this, and then your thumb points mutually perpendicular to both of those vectors and will point in the direction of the resulting force. So what we know is that the direction of this force is going to be out of the board. So if I called this X and called this Y, then out of the paper here would be the Z direction. So I'm just going to say I times B times K hat for the Z direction times the integral of DL. But there's another problem, because the B and the L do not necessarily sit right at perpendicular angles to one another. And we also know that the cross product, though we now have the direction for it, we don't really necessarily have the magnitude, because remember, A cross B has a magnitude of A times B times the sine of the angle between them, which in our case is actually called phi. Actually, no, that's not phi. I'll call it theta. Okay, the angle between them, in fact, is this angle right here. That'd be theta. Okay, so I'm going to put on the end of the sine theta. And of course, the sine theta, that's not going to change either. So now I've got IB, integral of dl is just going to be L times the sine of theta. So if you have B and L in two different directions, say this is dl in this direction, and let's say B is in this direction, and this is the angle theta, then the force acting on them would be, assuming again that this magnetic field doesn't change over the length of it and it's an appreciable length and it's all straight, then you get F is just equal to I times L times B times the sine of theta, or since my name is Billy, I'll say F equals Bill times sine theta. Okay, and of course the right hand rule, which is a different one than we had for the current in the wire. Again, the right hand rule applies. DL, that's the first vector in the IDL cross B. My pinky's parallel to it. My index finger points towards B, and then my thumb, being perpendicular to both my index finger and my pinky, points straight up, and that's the direction of the force. So in this case, it would have been K hat. So that's how we can actually compute the force on a wire immersed in a uniform magnetic field if the wire is actually straight and there's a specific angle. So if we imagine as an example, let's give you one hardcore example now. Let's imagine a wire carrying a current of, now I'm going to use a big number here, let's say 30 amps. That's a big, big current. And let's say it's in a magnetic field that is, of course, uniform. And the magnetic field makes an angle of, let's say, 36.87 degrees with the actual wire. So 36.87 degrees is the angle between L and B when they're tail to tail. And I would like to know what the force on this is. And let's say the wire has a length L equal to 1 meter. Okay. So at least that's the part within the magnetic field that we're discussing. The magnetic field, I'm going to use the unit of Tesla, which is the typical unit in the SI system. And we're going to say its magnitude is in fact 1 Tesla. So what is the force? F equals question mark. Well, F is equal to Bill times the sine of theta. So in this case, B is 1 Tesla. I is 30 amps. And L is 1 meter. And theta is 36.87 degrees. And of course, the sine of 36.87 degrees is actually 3/5. So we're going to say the actual magnitude of this would be 3/5 of 30 times 1 times 1. 30 times 3/5, 30 divided by 5 is of course 6, and then I multiply that by 3, that'd be 18. So it's going to be 18 newtons is the result. So that's sort of the simplest example of a force acting on a magnetic field. Remember, we've talked about the Earth's magnetic field, how wires carrying current create a magnetic field, what directions those fields point in. Mentioned that the unit for the magnetic field is the Tesla, T-E-S-L-A, named after Nikola Tesla. And it's actually a big quantity. In fact, the Earth's magnetic field is about 1/10,000th of that, and that unit's called the Gauss. The unit of the Earth's magnetic field is about 1 Gauss, whereas a Tesla is about 10,000 Gauss. So I think that's enough to get you started on this first part of magnetism. I hope that helps.